Welcome to our video. In this video, I will introduce our research paper titled NIL, Large-Scale Detection of Large Variance Clones. First of all, I will explain what a large variance clone is. A large variance clone is a kind of code clones that are generated by inserting or deleting many program statements in various places in a copy and pasted code fragment. As a result, a pair of large variance clones includes many uncommon program statements. So it is difficult to detect large variance clones more than general clones. This means that there are a couple of issues with prior detection techniques. The first issue is prior large variance clone detection techniques are not scalable. They are up to 10 million lines of code, or they require a long time to detect large variance clones. Another issue is scalable clone detection techniques cannot detect large variance clones. They can detect only lexically different clones or strongly similar clones. So we propose a scalable large variance clone detection technique. In this research, we propose a method-level clone detection technique using lexical information. To detect large variance clones, our technique measures code similarity using the longest common subsequence of lexical sequences. To realize scalable detection, our technique narrows down clone candidates using n-grams and inverted index of lexical sequences. Here is a sample pair of Java methods. This is the extracted lexical sequence. And the LCS is highlighted like this. In this research, we detect large variance clones using LCS of lexical sequences. But performing LCS algorithm for all method pair is not scalable. So we leave as clone candidates those method pairs whose n-grams have more than a threshold in common. Inverted index is used to speed up this process. Our inverted index is an associative array where a key is an n-gram and the value is a set of methods, including the n-gram. Here is an example. Method 1 includes token sequence of ABC, and method 2 includes a token sequence of DAB. If we make bigrams from these methods, AB and BC are extracted from method 1, and DA and AB are extracted from method 2. In this case, our associative array is constructed like this. If a query BC comes to this associative array, its output method 1 quickly. But using n-grams and inverted index, we can check whether a given two methods share enough tokens without calculating longest common subsequences. Here is our experimental result on effectiveness of our approach for speeding up. By using n-grams and inverted index, we could avoid calculating LCS more than 99 method pairs. We have published our tool NIL on GitHub. If you need a clone detector for your research or work, I hope you will include this tool in your selection. Next, I talk about the experiment on precision of LV clone detection. In this experiment, we detected clones with our NIL and two prior tools, LV Mapper and CC Aligner. Then we checked the detected LV clones manually. Here is the result. The number of LV clones detected by NIL and LV Mapper is comparable, but NIL's precision was the best of 87%. Next, I talk about the experiment on recall of LV clone detection. In this experiment, we randomly inserted 1 to 20 program statements into target methods to create a true clone dataset. The generated method by such insertions were used as clones of their original methods. Here is the result. X-axis is the number of inserted statements, and the y-axis shows the recall value. We can see that NIL's recall keeps 100, while LV mapper and CC aligner have lower recall when the number of inserted statements increases. Next, I talk about the evaluation of general clone detection. In this experiment, we use big clone eval to automatically measure the recall of clone detection result. We also measure precision based on our manual checking. Clones can be categorized into type 1, type 2, and type 3 clones. We measured recall and precision for each category. Here is the result. I will talk about a couple of remarkable results. First of all, NIL has a high recall of 96% for type 2 clones, even though it does not normalize identifiers in the source code. The second one is LV mapper and CC aligner had low precision, while NIL has high precision of 94%. The last one is Sorcerer CC and NICAT had a high precision, but their performance for moderately type 3 clones is not good. Next, I talk about the evaluation of scalability. In this experiment, we prepared a dataset of 1 to 250 million lines of code. Then we executed the clone detection tools on each dataset. Here is the result. The runtime of NIL is the shortest for all the input size. CC aligner and NICAT were not able to complete detecting clones from the large input size. Here is the conclusion and future work. Thank you very much.